Swayam Prabha. Digital India. Educated India.
Hello everyone. So today we will again continue with the sampling. In last class we have discussed the different types of sampling technique, like statistical, non-statistical. So non-statistical like are of two types we have mentioned: haphazard sampling and judgmental sampling. Now we will discuss some specific type of sampling for fibers, because as I told, we will focus mainly on textile material. So earlier sampling, statistical and non-statistical samplings are their broad classification where any material can be sampled, including textile material, as I have given example. Now, specifically for fiber sampling, the methods are classified into two parts. One is called numerical sampling, where the samples, the fibers are taken, like this is a fiber. We have to actually follow certain norms where the fibers are taken out, the specimen are taken out with a strictly as per the proportion of the fiber. So this is the norms we use here. So suppose here the fibers are longer fibers, medium length fibers and short fibers are distributed, and we have to select the fibers specimen in such a fashion. Suppose here 4 long fibers, 4 medium length fiber and 4 short fibers are there. That means 3 different types of fibers are there. Okay, so long fiber, medium length fiber and short fibers are there. So total 12 fibers are there of 3 types. Now if we want to take specimen or sample from this bulk, say 3 samples, if we want to take 3 fibers, if we want to take, where 1 long fiber, 1 medium length fiber, 1 short fiber should be there. That means the proportion of fiber length should be there exactly. In that case, it will be called as numerical sampling. What does it mean? So here the proportion of fibers were 1:1:1. Okay. If we take the 3 fibers out of that, so 8 fibers are remaining. That means 2 fibers of longer length, 2 fibers of medium length and 2 fibers of, so 6 fibers are there. So here remaining 9 fibers will be there. Out of this 9 fibers, 3 and 3 fibers are there. So again the proportion will remaining fiber will be 1:1:1. That means when we are taking out the specimen or taking out the sample out of the population, the proportion of the population remains same. So that is strictly meaning of the numerical sampling. Proportion is, that means we are not disturbing the remaining population when we are taking the sample, okay, which may not be actually always true, but in literally it means, it's basically mathematically this is the actual meaning, but actually it's not possible, okay. What it actually means here, when we take the sample from the population, we are not disturbing the population proportion, basically. We are not disturbing the population. That means we are selecting the fiber irrespective of fiber length. No biasness is there. There is no biasness. And next method is, it's called biased sampling. Biased sampling means when we are taking the sample from the population, that means selection is actually, it's influenced by some factors, and which, that is, the selection is influenced by some factors other than the chance. If it is chance factor, then we will call it as randomness, okay, random sampling. But other than the chance, there are some factors, and this sample which is not truly representative of the bulk, and this is true for fiber sampling from some tuft, like in fibrogram. Fibrogram instrument, where when we take the fiber specimen from the surface, if I am trying to take the fiber in this fashion, fringe I am taking, what are the factors here? Let us see. These are the fibers here of different length. Small fibers and short fibers are there. Now when we are taking this fiber from the surface, by picking from the surface, this is the fringe, which when we are taking the fiber, this type of fringe we are taking, here the longer fiber has got higher probability of getting selected. That means, I'll just explain. So this is called bias sampling. So if we take the longer fiber specifically from here, that means long fiber proportion is coming out and short fibers proportion are increasing here in the remaining bulk. So this is actually not numerical sampling. But when we take the sample, fiber sample from the sliver, this is sliver. Let us see this is one sliver. In this sliver, if we take fiber by gripping at the tip of from the, now if we take these fibers and removing these fibers from this portion, the remaining fibers are not disturbed. And if we assume that in normal sliver, our assumption is that fibers are distributed randomly along this sliver, irrespective of the length, they are distributed. So if we pick the tip of the fibers at the edge, the chances of selection of short fibers, long fibers are same. In this range, I am selecting the long fiber, short fibers, medium length fibers. But on the other hand, if I take the fringe from this bulk and gripping from the surface, the longer fibers are having greater chance of being selected. So the automation in, say, high volume instrument, particularly the fiber fringe in fibrogram, there the selection process is that you take the this tuft and we select from the top. Whatever fringe we are taking there, it's length bias sampling. Before we discuss the fiber this sampling here, so let us try to understand what are the different causes of biasness in sampling. So bias due to the physical characteristics. Longer fiber always has greater chance of being selected. Like if we see, now if we see, this is the fiber from the surface. At the surface, these fibers are arranged in this fashion. Now if I grip in this point, or I can grip from this point, so this is A or this is B, whatever we do, if we grip select the fiber gripping this point, the longer fibers are, all the longer fibers are selected. But this short fiber is selected only for A, with this A, but with B it's not selected. So depending on the fiber length, the longer fiber has got higher proportion of being selected. Suppose if I grip at point A or point B, so all the long fibers are selected. So this is due to the physical characteristics of the fiber. It automatically generates the biasness. Position relative to person. Okay, the lab technician may pick the bobbin from the top. So there is a heap of, say, 1,000 bobbins. So he is not trying to take the sample from the bobbin from the core or inside the heap. He will pick the sample from the top of the heap, and that will actually generate the biasness. Subconscious biasness. Like I am going to the shop floor, there are some damaged fabric is there, or there's a fresh fabric. I want to take the fabric specimen. Some damaged or dirty fabrics are there, dirty cones are there of some way. I will not take that one. That's my subconscious mind. I will try to take the fresh one or some good looking one. This is actually generating the biasness. And sometimes conscious biasness means, okay, I will take the best one and try to test. Okay, I will take the worst one. The ring frame where vibration is more, I want to test. So consciously I am trying to test for certain purpose. Okay, but that may not be representative of the population. So while sampling, we use different terms. Okay, first term is the consignment. Like industry A is producing yarn and sending to industry B, which is the producing fabric. Weaving industry and spinning industry. And say there are 10 tons order are there. It consists of say 2 tons of 30 count, 4 tons of 40 count, and 2 tons of 10 count, okay, and 1 ton of say 20 count, 1 ton of 50 count. These are the total requirement, and they are produced, and this 10 ton, this is sending to industry B at a time. So this is actually called on consignment. This may require say 10 truck or 10 container, doesn't matter. It is going, it is sending in a particular day to another. This is called consignment. It may contain different lots. What are the lots then? This 2 ton of 30 count is a lot. 4 ton of 40 counts is a lot. These are the lots, different lots they are producing. Okay. Test lot or batch. So this is one batch of 30 count, 50 count, and when it's going to company B at a time, this 1 ton of 50 count or 1 ton 20 count, 2 ton 10 count, these are called one whole population. 1 ton of 50 count is a population. 2 ton of 30 count is a population. Okay, and this is one batch. Now next time next, say after say 10 days, this is again sending the material, same proportion they are sending, 10 ton material is sending after 15 days, 10-15 days, but that will be treated as different lot, different population. Okay. And then, so this lot or population has come. So in that population, you have got different types of population, different batch. Now, for testing, you have to take the sample. So this is called laboratory sample, and laboratory samples has to be derived from the lot. We will definitely not mix the 50s count to 10s count with this, we will not do. So they will be treated separately because they are different lots, but we will select sample from a particular lot. Say I want to test count of 30s count, strength of 30s yarn. So I want to test, say take the, from the, by statistics I know I want to take the 20 bobbins, 20 cones, 20 cones out of say 2 ton yarn. 2 ton is my population, 20 is a cone which is sample, and this, for sampling we have to adopt the technique which we have already discussed in last class to get the laboratory sample. So we have got 20 bobbins, and this 20 bobbins we are not going to test entire bobbin. So the proportion, the portion which is being used for actually testing, that's called laboratory specimen, test specimen. Suppose we want to test the micronear value. So laboratory sample is maybe 1 kg. From that we will pick say 5 gram by some method that we will discuss, and this 5 gram is used for micronear value. This is called test specimen, the portion which is being used for testing, evaluating the characteristics. So a sample of textile material, it should be representative of the bulk as we have discussed. So sampling technique is extremely important where the variability is high. This is very important. Like a company which is making a particular say glass ball or some molded item, a molding will create a material, a product of almost equal size. Okay, suppose this mouse, one company is producing, which has got a particular mold, a shape, and it is producing. Now, we may not need that many sample or specimen to test its mass or its dimension, because when we are sure that its variability is very less, almost zero variability, then our number sampling technique will be entirely different, or number of specimen will be different. But when the variability is very high, particularly textile material, there the sampling is extremely important, and we have to be very careful during sampling. Now, for cotton fiber from bale, what are the sampling stages? First stage is that bulk sampling. Bulk sampling means, suppose I have got say 200 bales. We have to pick the bulk, say 1 kg sample from the of cotton from 200 bales. So it's not a good idea to open up all the bales and take the sample. So for that we need a specific number of, we have to open a specific number of bales, and there are, it is specified. Then from that, say 1 kg or 2 kg fibers, we will take by using certain technique, we will derive the basic sample, and from basic sample we will take the laboratory sample, and from laboratory sample the test specimen is derived. Now there are guidelines when a large number of bales are there. So we have got say 200 bales, okay. So few bales are to be chosen at random. So again, which bale has to be selected, that what are you going to use? We will again use the random number, random sampling. So bale, from bale we are taking the random, randomly selected bale, and from each selected bale we will take the small quantity of specimen and then mix together. So when we are using the random number or random sampling, there we are not introducing any biasness. Then from bale we are also taking the specimen, this small sample, which is again randomly, as we have discussed, that the fibers from different portion we will take, which will be representative sample, and this is the guideline. Typically in the industry this guideline is followed. So how many bales has to be opened? If we have up to 50 bales, we will take the specimen from the 2 bales, randomly selected 2 bales, okay. Then 51 to 100, 4 bales, like that, and above 1000, 40 bales we will take. 40 bales has to be opened, and then we will take the sample, so that there is a total entire randomness. Then basic sample, from the bale you have selected bale, then from the bale we will select, from each bale we will select a small quantity, and then we will mix thoroughly, okay, and proper homogeneous sample has to be prepared, and total quantity of this basic sample should be around 1 kg. 1 kg sample we are taking. from 1 kg sample, so 1 kg we have got, from 1 kg we have to extract again small quantity which will be laboratory sample, maybe this much sample, okay, depending on our test, say maybe 5 gram sample, 10 gram sample. And to do these things we will follow a certain norms where total randomness is actually there, no biasness. Like suppose this is a sample which is basic sample, say 1 kg sample. From there we are trying to extract the laboratory sample, say maybe 200 to 500 milligram, or maybe depending on the type of fiber. So HVI pair sorter, so maybe 5 gram sample or 10 gram sample is okay. So what we do, this is 1 kg sample, then we randomly, after mixing, we randomly divide it to different zones. This is different zones. It's called, that's why it's called zoning technique. Different zones we have to. Even after randomly mixing, then these zones are there. It has got say 1 kg or 2 kg fibers. Now we have to reduce it. So we can simply take 5 gram fiber. That's way. But that is not giving the randomness. The technique is saying, in this zoning technique here, you take zone 1, then you divide it and keep one for the sample and rest you discard. Again you take next one, keep this, other you are discarding. So this is in one step you are doing, and next step again you are doing the same thing, you are repeating, and then gradually it's a reducing. What you are doing, in the first time you are doing lengthwise, then second time you are doing removing this way. So in every way you are trying to incorporate the randomness. Okay, but this zoning technique, there is no strict norms. One can frame. Okay, here I have given example of, you are using, say you are taking a removing from left hand, next time you are removing from right hand. Any way you can do. Okay, this is, you are getting the laboratory sample. I will discuss the zoning technique subsequently. And one approach is that it's a critical difference. Concept of critical difference is that it measures the difference between two values which arises solely due to unavoidable causes. Okay. So when the difference between the two values exceeds this limit, then we will call it as statistically different. Okay, it's a very quick method, okay, and used mainly for fiber, cotton fiber. It's a critical difference we can use in some other parameters also, but for cotton fiber it's used in industry where you don't need to calculate. So significance test we will discuss, where you need to test the statistically. But here critical difference, that reference table is given. Simple what we have to do? We have to simply compare with the reference table, where the table is given for different types of fiber properties. Here, if you see, for HVI testing, high volume instrument or fibrogram, so 2.5% span length, where you have to take the 4 combs, 4 specimen you have to take. What is comb here? As I have told, you take the specimen from this fringe is, it's called one comb. Okay, so such 4 combs if you take, if the critical difference is, it comes less than 4, that means there is no variability. Okay, its variability accepted. And here only due to the random factor. Uniformity ratio specimen is 4. This is the standard plug. So these are the percent of critical fiber length at 3 millimeter gauge length, maturity coefficient, trash content. So these are the different norms are there. For yarn properties also, the critical difference, number of tests is given. Okay, and these are the typical critical differences are given. Okay, so for length, Lee test, Lee strength, Lee count, Lee strength, single yarn strength. These are the yarn twist, double yarn twist. So when you are single yarn twist, the critical difference acceptable is this 3.4. Double yarn, it will be reduced. Okay. So what is that? How do you calculate critical difference? Now let us take one example. So for cotton, you have got 3.4 and 3.6. From 2 sources you have got cotton fiber. One is 3.4 micronair, another is 3.6 micronair. Now let us see go back to the table. Micronair value, critical difference is 6. 6 is the standard value, and with the 4 plugs percent, 4 tests you have to do. Now here if you see, one sample you have got 3, another sample you have tested 6, whether there is a real difference or not. So you take the percentage, it's very easy. So this difference divided by mean micronair. So mean is here 3.4, 3.5, 3.4 and 3.6 mean micronair. So critical difference is. So what is critical difference then? You are actually here, you are trying to measure the difference, significant difference between 2 mean value, 2 values, and then the mean of these 2 is here 5.7. Now when it is coming to 5.7, using 4 plugs, so then we can say, we can call it as there is no significant difference between 3.6 and 3. So we can use this as a particular lot.